Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be going through chapter 5.2 and looking at properties of linear transformations. In chapter 5.2, we will continue our study of linear transformations by learning how its image and kernel provide information about the nature of the mapping. Consider a linear transformation T mapping vector space V onto vector space W. One way to consider this mapping graphically is to consider this graphic. Our starting vector space V can be projected or mapped into our codomain W. However, sometimes our image is not all of your codomain. It may just be a subspace of your codomain, a subset. Recall, the image of T is the set of elements in W that are associated with a V in V, such that W is equal to T of V. Let's look at some definitions to help us get started. The image of a linear transformation T is always going to be a vector space, so that it satisfies the closure of vector addition and scalar multiplication properties that we learned in chapter 3.5. An injective mapping is represented by a one-to-one function. That is, different inputs give rise to different outputs. This is a concept you'll remember from college algebra. One-to-one functions are functions that possess an inverse. There are also functions that you recall pass the horizontal line test. Consider two functions, maybe y equals x cubed. And maybe y equals x squared. Let me see if I can draw that a little bit better. One of these two functions is injective, or put another way, one-to-one. And it would be the one that passes the horizontal line test. However, the terminology we use is different inputs give rise to different outputs. In which case we would say x cubed, this is our one-to-one function. Every input I give you, regardless of which x value it is, gives rise to a different y value, a different output. So another way to say this is this function is injective. While the graph of y equals x squared is not one-to-one, because different inputs, for example, y equals 3 or y equals negative 3, both give the same y value of 9. So different inputs do not give different outputs. There's a repetition. In which case this function is not injective. A surjective mapping is represented by a function whose image is all the codomain. If the image is not all the codomain, we generally want to be able to describe it though. But a surjective image is when your image is all of your codomain. Now if I were to look at the graphic I showed you earlier, this is not the graphic of a subjective transformation. Maybe a graphic of a subjective transformation might look something like this. Here's your domain. Here's your codomain. And maybe you're here, your image of T is all of your codomain. This would be an example of a subjective mapping. Sorry, not subjective, surjective. This is a surjective mapping. When the image is all of the codomain. And then lastly, the rank of a linear transformation is the dimension of the image of T. So recall from chapter 3.6 that the dimension of a vector space is the number of vectors needed to span that space. So here for us, the rank is the number of vectors needed to span the image. Let's look at some examples. Consider the transformation T mapping R3 onto R3 defined by the function T of xyz is equal to xy0. You'll recall this transformation we looked at in chapter 5.1. And our first question is, what is the image of T? So recall, this transformation takes any particular element in our domain, an element of R3, and maps it into our codomain, which is also R3. So a typical element would be x, y, z, so it'd have some x coordinate, some y coordinate, and some z coordinate. And what this transformation does is it makes the z coordinate equal to 0, which projects this point vertically downwards until it hits the xy plane. It gives us the point x, y, 0. If we imagine this happening for several points in our domain, all of these points would be projected downwards. And we can visualize that this will end up covering the entire XY plane. So to be specific now, our image, either you can say it's the XY plane, in R3, or you can describe it in set notation as the set of items that look like X, Y, 0, such that X and Y are elements of the real numbers. It is important that you do not say this is R2, because our elements are not, the things we get back are not two-dimensional elements, they are three-dimensional elements. They have three components in them. Okay, next one. Is T injective? Is it one-to-one? Does every input give rise to a unique output? And here I want to say no. Because consider 2 points that live above each other vertically. 2 different points that live on the same vertical line. Maybe you could say the points 3, 1, 3, and maybe you could give another point. Let me get rid of this ordered pair here, ordered triple. Maybe another point might be 3, 1, 1. All that's different with these 2 ordered triples is our z coordinate is different, giving rise to different vertical heights. And if you were to look at T of 3, 1, 3, or T of 3, 1, 1, these would both equal 3, 1, 0. So that different inputs do not give rise to different outputs. Okay. Is T surjective? Is its image all of the codomain? No. Because the image of T is not equal to R3, which is your codomain. Remember, the image was only the XY plane in R3 and not all of our codomain. What is the rank of T? Remember, the rank of T is the dimension of your image. Our image is the XY plane. And the XY plane, you want to notice, is a two-dimensional image. So the rank of T, this is the dimension of the image of T, and this is equal to 2. Now I pose a question. What if we say the transformation was written as T mapping R3 onto R2 defined by this function? Notice how similar this transformation is. We changed our domain. I'm sorry, the domain stayed the same, but we changed the codomain to R2, which means we also had to change our function. Now we make it so that we just get rid of the third coordinate. Before we made it equal to 0, but there was still 3 components to our vector. Now there's just 2 components, so now this is how we're mapping it into R2. How would this change some of the statements we made earlier? For example, part A. Would it change the image? Well, not really, but slightly. Now I would say the image of t is R2, or the xy plane, but I don't have to say it's a plane in R3 anymore. It is all of R2, because we're mapping it into R2, we're mapping it to ordered pairs, and we do get the entire xy plane. Part B, is it injective? No, that did not change. Different inputs still give rise to the same output. Part C, is it surjective? Now I would say yes, because the image of t is equal to R2, which is our codomain. So notice that changing how our transformation is did change our statements about the image and whether or not it was surjective, but it did not change our decision about being injective. Let's look at another example. Consider the transformation T mapping R2 into R3, defined by the transformation T of V is equal to AV, where A is your matrix of transformation. So multiplying by A is what takes you from R2 into R3. Another way I could write this is to say that T of, now remember we're starting in our domain, which is R2, so maybe an XY element. And it maps it into R3 by multiplying by this matrix of transformation. Now, when I multiply this matrix, which is a 3 by 2 times this 2 by 1 vector, we should get back an output. And there's different ways you can consider multiplying this. I'm actually going to write it a first way, and then I'm going to erase it and rewrite it the way I'd like to write it. If we recall how we did this initially, we said, let's take any particular row and multiply it by our column. Notice this would be x times 1 and y times 1. This would be x plus y. If I multiply the next row times this column, I'll get x minus y. And if I multiply the next row times this column, I'll get 2x plus y. And the way I'd actually like to write this is by writing it as two vectors where each is multiplied by one variable. So maybe I can write this as just x times the vector 1, 1, 2 plus y times the vector 1, negative 1, 1. Notice that written like this, we can sometimes refer to as a matrix multiplication as a linear combination of the columns of the matrix A. It's x of our first column of A plus y times our second column of A. So frequently when doing this multiplication, I won't write this middle step. I'll just write the matrix multiplication as a linear combination of the columns of A. Now, using this terminology, another way to talk about the image of this transformation is I could say that it's equal to the span of these two vectors. Remember, the span is all possible linear combinations of our vectors. Now, thinking about the terminology and the ideas of chapter 3, I would say, what is the span of these two vectors? Maybe our first vector 1, 1, 2 would be a vector pointing 1 in the x direction, 1 in the y direction, and 2 in the z direction. So it's a vector that from the origin points to this point in 3 space. The vector 1, negative 1, 1 points 1 in the x direction, negative 1 in the y direction, and 1 in the z direction. So it points here. And now I want to imagine all linear combinations, the span of these two vectors. And I would like to say the span of these two vectors will be a plane in R3 that contains these two vectors, all linear combinations of it. For example, if you did one of the first vector and one of the second vector, it would land you here. So I'm representing a portion of the plane that will be spanned by these two vectors. So one way to discuss the image of T is to say that it's a plane in R3 through the origin. However, if you've taken Calc 3, then you should recall how to describe the equation of this plane that's spanned by these two vectors. I'll leave it for you to consider that, and if you don't remember how to do that, you might want to review your notes from Calc 3 to remember how to find the equation of this plane. But for our class, I'm fine with you telling me it's a plane in R3 through the origin. Is our mapping injective? Remember, to be injective means different inputs give rise to different outputs. Or, like in our example we did with y equals x squared, there's more than one way to get to y equals 9. So you can take 3 or negative 3. Both of these will get you to y equals 9. So to put it another way, can you use different inputs and get the same output? Or consider our picture here. Are there different ways to get to this point right here? And I think no. The only way to get there is to do one of your first vector, call this v1, and one of your second vector, v2. That's the only way to get to that point. Or to put it another way, we can say, because our two vectors that we're given are linearly independent, they're not multiples of each other, that'll allow us to say this is injective. So yes, because the vectors are linearly independent. Okay. Is our mapping surjective? Here we want to say no, it's not, because the image of T, remember, to be surjective, your image has to be all of your codomain. Here, our image is not all of R3. It's only a plane through R3. So no, because the image of T is not equal to R3. And And lastly, what is the rank of our transformation? Now remember, the rank is the dimension of our image. Our image is a plane in R3. Our image is spanned by these two linearly independent vectors. And because it's a plane, because we have two linearly independent vectors, this tells us our rank of t is equal to 2. Okay, let's move on. And let's add a little bit more theory to our linear transformation idea. And let's talk about the kernel of a linear transformation. Recall from the definition of a linear transformation, T mapping V onto W, that the zero vector in the domain V must get mapped to the zero vector in the codomain W. Or to put it another way, T of 0 has to get mapped to 0. Our question is it possible that other vectors of the domain can get mapped to 0 as well? Or specifically, the kernel of T are all of the little vectors in V that T of V is 0. Our graphic shows us that the kernel absolutely will take 0 and map it to 0. But the kernel is all of the vectors in our domain that could also get mapped to 0. There could be more than one. To tie this into previous ideas, this is the same thing as calling the homogeneous solutions. Of a problem. It's all the things where the solution is equal to 0. Along with us are two other ideas that are important for us to mention. One of them is referred to as the dimension theorem. The dimension theorem says that if you found the kernel and looked at the dimension of the kernel and added that to the dimension of the image, that would be equal to the dimension of V, your domain. So the dimension of the kernel plus the dimension of the image of T is always the dimension of your starting domain. And then there's also the kernel theorem, which says T is injective if and only if the kernel of T is the 0 vector. Remember, to be injective, it means that different inputs have to give rise to different outputs. Here we're saying that if there's more than one thing that goes to the kernel, then this is not injective. However, if the only thing in the kernel is the 0 vector, then we would be injective. Another way to word this is we could say the dimension of the kernel of T has to be 0. And this is not 0 the vector, this is 0 the scalar. Remember, the dimension is the number of vectors that are needed to span your space. Here we're saying it's 0 vectors. Okay, let's look at some examples. Consider our familiar transformation T mapping R3 onto R3, defined by the transformation T of xyz is equal to xy0. So recall, this is the transformation that takes an ordered triple in R3 and projects it down into the xy plane. and I want to know what is the kernel. What are the things that get mapped to 0? What are the things that get mapped to this point in our codomain? And I want to say the only thing that gets mapped to that, or the only things that get mapped to that point, are the things that live on the z-axis. Of course, they could live above the z-axis, or they could live below the z-axis. Anything on the positive or negative z-axis will always get projected onto the origin. In which case I want to say the kernel of t, you can say it as the z-axis, or you can say it's the set of things of the form 0, 0, alpha, such that alpha is a real number. Notice that this is an equivalent definition of the z-axis. Okay. Is t injective? Well, now we can say no. Remember, we can use the kernel theorem. T is injective if and only if the kernel of t is the 0 vector. Here, the kernel of t is not the 0 vector, it's the x-axis. So I can say no because the kernel of t is not only the 0 vector. Or you could also add to this the dimension of the kernel of t. So now think about the kernel of t. The kernel of t is the z-axis, but it's a line. It's a line spanned by this vector. And this vector is a line, and lines are one-dimensional. So we could say the dimension of the kernel of t is equal to 1, and we require the dimension of the kernel of t to equal 0. Now if I add a little bit of extra to this, I could also apply the dimension theorem. Since we know the dimension of the kernel is equal to 1, we should also be able to refer to the dimension of the image of t. And remember, our image, we've looked at this problem more than once, ends up being the entire xy plane in R3. But it's the xy plane, and this is a two-dimensional image. So notice now that the dimension of the kernel plus the dimension of the image, the sum of these two spaces, is equal to 3, which is the same as the dimension of the domain. This is great because if you ever know the dimension of the kernel, you automatically have to know the dimension of the image because it has to be whatever's left of your domain. Let's look at another example. Consider the transformation T mapping R3 onto R2 defined by T of V is equal to AV, where A is your matrix of transformation. So A does your transformation of mapping your domain in R3 to your codomain in R2. Now, one way to visualize this is to consider what T of a typical element in your domain looks like. And since we're starting in R3, we would start with an ordered triple X, Y, Z. And T maps this ordered triple into your codomain R2 by multiplying by this matrix. And I would like to think of this matrix multiplication as a linear combination of the columns of A. So this will be X times your first column plus y times your second column plus z times your third column of A. Oh, I think I put a number wrong. That last column shouldn't be 1, 5. It should be 2, 5. It's a linear combination of the columns of A. Now, with this random transformation, I'd like to be able to do the same as our last example. I'd like to be able to talk about what is the image of T, what is the kernel of T, is this mapping injective, is this mapping surjective? And there's not one unique way to go through and answer all of these questions. There is different ways to answer it. But I'm going to start with the image. Remember, the image of T is going to be all the possible linear combinations of these three vectors. Or to put it another way, it's the same as the span of these three vectors. In which case, now I'm looking at these vectors one at a time. And I'm considering, are these vectors linearly independent? Notice if you grab just the first vector and ignore the other two, 1, 2 is one vector, it's independent. Then consider adding the vector 1, 3. Is this a multiple of the first vector? And you want to say no, 1, 3 is not a multiple of 1, 2. However, the third vector is a linear combination of the first two. Technically, you could say v3 is equal to v1 plus v2. So the third vector is not linearly independent. But we do have two linearly independent vectors. Now consider we have two linearly independent vectors and we're taking all possible combinations of these. Will these two vectors span R2? And now I'm referring again to back in chapter 3.6. Since we're mapping into a two-dimensional vector space and we have two linearly independent vectors, we can say that the image of T is all of R2. And I can say because the span of 1, 2 and 2, 3 is equal to all of R2. These three vectors cannot be a basis because they're not all linearly independent. But if the first two vectors span all of R2, then all three vectors will span R2. And so our image is all of R2. Now I can't tell you the kernel just yet or whether it's injective, but I can talk about surjectivity. Remember, being surjective means your image is all of your codomain. Here we can say yes, because the image of T is equal to R2, our codomain. Well, we probably even add to this now, what is our rank? Remember, our rank is the dimension of the image of T. Here, the dimension of our image, because we're talking about R2, is 2. So now I could probably make some statements about the kernel and injective. Now remember what the kernel theorem said, that the dimension of the image plus the dimension of the kernel had to equal the dimension of your domain. If the image is two-dimensional, that means the kernel has to be one-dimensional. It has to be a line, in which case it's not only the zero vector. So I should be able to say that there's something in the kernel other than the zero vector. But let's go find that something. So now recall, the kernel of T are all the vectors V that are in your domain R3 such that T of V or AV is equal to 0. They're the things that get mapped to the 0 vector. They are the homogeneous solutions of this system of equations. So let's go find the homogeneous solutions to this system of equations by considering what our augmented matrix would look like. Here our augmented matrix would be the columns of A, 1, 1, 2, 2, 3, 5. Remember, I like separating my right-hand vector with a dotted line, 0, 0. Now, I would like to write this matrix in RREF form. And I think we can do this with just one row operation. If we went -2 times row 1 and add that to row 2. Of course, we could use our calculator, but I think this is faster just doing it by hand. When doing this row operation, we would not change the first row. And -2 times that added to that is 0. -2 times 1 added to 3 is 1. -2 times 2 added to 5 is 1. -2 times 0 added to 0 is still 0. It looks like we have one more row operation to do. Let's now go negative row 2 plus row 1. Here I'm using this pivot to make the value above it turn to 0. So 0, 1, 1, and 0, your bottom row will not change. And you go negative row 2 added to row 1, that's 0, that's 0, that's 1, and that's 0. Notice that our matrix written in RREF has 2 pivots. These would be the x and y variables that we would have started with, and it has one free variable. This would be the z variable. If we're recalling ideas from chapter 3, because we have free variables, we have multiple solutions to the homogeneous equation. So let's go find those homogeneous solutions. Recall from chapter 3, the way that we did this is we rewrote our matrix back as a system again. Represented by x plus z equals 0, y plus z equals 0, and z is your free variable. And in chapter 3, the way we resolved this is we let their free variable be some other letter like t, and then we solved for our pivot variables in terms of our free variable. So instead of writing x plus z, I'm going to write x equals, I'll move the z to the other side to make it negative z, but I'm going to let it be t. So negative t. Y is equal to negative t. Z is equal to t. Or if I factor out the common variable t, we can write the homogeneous solution as t times the vector -1, 1, 1. this would have been the homogeneous solutions to the matrix equation AX equals 0. This is what the kernel is. So now the kernel are all vectors that look like this homogeneous vector. So maybe we can say the kernel is the set of vectors that look like t times -1, -1, 1, such that t is an element of the real numbers. These are all the things that get mapped to 0. And because the kernel of t is not only the 0 vector, there's other things there. I will say that it's not injective because the kernel of t is not only the 0 vector. And as a final note, just to mention our kernel theorem, this is a valuable tool to keep in mind. We should know from here that the dimension of the image of t, we said, is 2. The dimension of the kernel of t, and because the kernel of t are all multiples of this vector, which is a line, its dimension is 1. And the sum of these two dimensions is 3, which is the dimension of your domain, since we started with things out of R3. Okay, let's look at one more example here. Now let's consider the mapping going from R4 into R2, defined by T of V is equal to AV, where A is our matrix of transformation that takes us from our domain, R4, and maps us into our codomain, R2. Now, like before, I would like to be able to find the image, the kernel, whether this is injective and surjective, like in our last example. However, I'd like to give you the opportunity to work this on your own. So if you could, pause the video, rework this example like we did the last one. After you're done, come back and we'll see how you did. I'll see you in a moment. Okay, I hope you paused the video and worked on this example. Let's see how you did. I would like to first rewrite our transformation. Remember, the way we did the last time is we said, let's look at t of an element in our domain. And there's different ways to write this, but I'm going to write it as x, y, z, and w. Sometimes our author uses x1, x2, x3, and x4 as subscripts. Now t maps this element in R4 into R2 by multiplying by this matrix of transformation. And I would like to think of this matrix multiplication as taking a linear combination of the columns of A. So this would be x times our first column, y times the second column, z times the third column, w times our last column. It is the linear combination of the columns of A. And like before, I'd like to be able to discuss what is the image of this transformation, what is the kernel of this transformation, is this mapping injective, is this mapping surjective? And again, you don't have to go in any particular order. With some of these problems, I can pick off what the image is by visual inspection. Remember the image, this is going to be the span of these vectors. It's going to be all possible linear combinations of the columns of the matrix A. And because we're working in R2, I can visualize, or I can by inspection determine if enough of these vectors are going to be linearly independent to span all of R2. So notice that the first vector, 2, -1, if you ignore all the rest, 2, -1 is a linearly independent vector. Is the second vector independent from the first? And here I want to say no. Here it actually looks like this is -2 of the first vector. So I would say -2 of the first vector is the second one. And so it's not linearly independent. Okay, how about the third vector? Is it linearly independent of the first? Is the third vector a multiple of the first vector? And I want to say no, the third vector is not a multiple of the first, which means these two vectors are linearly independent, and we have two linearly independent vectors getting mapped into a two-dimensional codomain. That's enough for us to say that our image is all of R2, and I would like to say because the span of 2, -1 and 3, -2 is all of R2. If these two vectors span all of R2, then that will cover will be our image. This is also enough for us to say that yes, our transformation is surjective because the image of T is all of R2. Which we should be able to say, if we're thinking about the dimension theorem already, the dimension of our image is a two-dimensional space. But we're starting from a four-dimensional domain, which means the kernel theorem would say that there has to be two things in the kernel. There has to be two things in the kernel. But let's go find the kernel. So now remember, the kernel of T are all the little vectors V in R4 such that T of V or AV is equal to 0. And written this way, again, we're looking for our homogeneous solutions. We're looking for the things that will give 0 back, all the things that get mapped to 0. These are the homogeneous solutions of this system of equations. Which I'm going to find by writing our augmented matrix. So our augmented matrix, I like writing it as the original columns of our matrix A separated by a dotted line, which is going to be the right-hand side of our system of equations. Now I'm going to help us out with the RREF here to save us time. If you did the row operations by hand, or preferably using a calculator, your RREF of this matrix should look like 1, -2, 0, 3, 0, 0, 0, 1, 0, 0. Here we should identify that we have two pivots. These would be the x and z variables. And we have two free variables that would be represented by y and w. And because we have free variables, that tells us we're going to have multiple things in our homogeneous solution. Let's go find those homogeneous solutions. The way we did this in chapter 3 is we now wrote our matrix of RREF back as a system of equations. And this would be written as x minus 2y plus 3w equals 0. Now I'm going to write the next variable y. This we knew as a free variable. Now our second row of this matrix says that z is going to equal 0. And I want to line this up with where z would have been. And then also we had w was going to be a free variable. And following our model of chapter 3, we'll introduce other variables to represent this. Maybe we'll let s be our y free variable and t be the w free variable. And now let's solve for our pivots in terms of our free. So remember, x was a pivot, z was a pivot. So let's move all our free variables to the right hand side and replace them with the corresponding free variables that we introduced. So I'm trying to say, let's let x equal, we'll move the 2y, it'll be positive, so it'll be 2s. Move the 3w over, it'll make it negative. We'll call it minus 3t since w is really t. Y is equal to s. Z is equal to 0. W is equal to t. Or if we're factoring out our individual variables and writing this as a linear combination, then I'll write my x homogeneous as s times the vector 2, 1, 0, 0. These would be the coefficients of these s variables. Plus t times the coefficients of our last variable, negative 3, 0, 0, 1. These are our homogeneous solutions, which happen to also be our kernel. So now our kernel, we can say they're going to be all the things that look like s times 2, 1, 0, 0 plus t times negative 3, 0, 0, 1, such that s and t are elements of the real numbers. It's all linear combinations of these two vectors. And because our kernel contains things that are not just the 0 vector, we can now say it's not injective. So no, because the kernel of t is not just the 0 vector. There are other things in the kernel. And I'd like to finish this off with a final note about the kernel theorem now. Remember, the kernel theorem says the dimension of the kernel of t, because the kernel of t is spanned by these two linearly independent vectors, its dimension is 2. And the dimension of the image of t, so remember the image of t we said is all of R2. So the dimension of the image of t is 2. And the sum of these is equal to 4, which is the same as the dimension of our domain. Okay. I would like to stop our video here. I have a couple more examples I want to work on with you, but I'm going to do those in another video since we're reaching 1 hour on this video now. So I'll see you in our next video, but I hope this is helpful.